Okay, so today we will touch upon a few remaining topics in ROS and, um, you know, uh, combined with the lecture today plus, I guess, 2 more lab sessions, and then we'll be done with covering whatever we need to know with ROS and move on to actually working with the real cars. And so, our intention is to make it as easy as possible to transition from sort of Turtlesim like activities to working on the real car, which is why we are taking a little bit of our time to cover some of those very, very essential ROS concepts. And so, in the same spirit as of previous few lectures, we'll cover some more critical aspects of the ROS Python API today. In particular, we will look at ROS services and ROS launch as the two sort of new things that we will have a deeper dive into the box. But with that, let's jump to the focus of this lecture, which is on learning about ROS services and ROS launch. So, so far we were covering slowly these ROS Python client libraries. We've seen many instances of how to publish, how to subscribe, how to form some messages and publish and subscribe over that. We had our listener and talker example in the previous lab session. In the lab session this week, we will learn about running some of these services I'm showing you today, plus also learn a little bit about namespace, launch files, and the concept of time in ROS, which we so far haven't discussed. All right, so we know how to run a package, how to create a package, how to handle a workspace. So far in ROS, I have been emphasizing that the mode of communication between any two nodes is this publisher-subscriber model, where a publisher, similar to the talker that we wrote or at least executed in the lab session, is just going to broadcast on some channel, which was chatter, I believe, and then we don't care how many subscribers there were. In fact, if the namespace of the ROS init node is set to be false, the anonymous field is set to be sort of true, not false, then you can have as many subscribers with the same Python script or ROS node script. But publishing and subscribing is not the only way to communicate between the nodes. It's the most useful and prominent way, but there is a more sort of traditional model of communication which ROS also supports, and sometimes this alternate method makes more sense or is more suitable to accomplish some sort of communication. And so this construct of communication is more similar to like a client server, a request response model. Okay, in a publisher subscriber, we don't have any kind of back and forth. It's sort of unidirectional broadcasting. But in this client server configuration, one node, which is the client, can actually ping a server for some service, and that server has to respond to this request, right? So it's bidirectional communication rather than this broadcast. And that is accomplished using something called ROS services. We've seen examples of this already when we called some services which Turtlesim offers. Okay, so we had a service, the teleport is like a service that Turtlesim node offers. And we've already seen examples of how to play with that. So why is this useful? It's useful, again, because sometimes you actually care that if I'm asking you for something or I'm sending a request for some functionality, I actually care your acknowledgement that did you actually do that? Because if you did not, then I might not be able to proceed with the rest of the stuff I wanted to do. Okay, so this is used less frequently. Like you can ask, okay, why isn't all communication using this client server? Because most of the time we care about these flows of data in forms of messages and topics from the sensors especially, but services are a way for having some specialized back and forth communication between dedicated ROS nodes, and you'll see examples of that on the F1tenth car as well. And so the way services are constructed is actually very similar to how messages are handled in ROS. In fact, the similarities are so startling that I will go over some of the same things that you have seen when we were discussing ROS messages. So for example, just like ROS needs a .message file for it to handle a particular message class, whether it belongs to a standard messages package or your beginner tutorial package, services also need some descriptive files which are .srv. It's a standard ROS. And so this SRV file can be in the SRV subdirectory of a package. And within that file, you are essentially defining the class of the service. So it will become clear when we look at an example. But before that, let's just get used to the idea of the difference between ROS service and the publisher subscriber. So service calls are bidirectional. You have a server and you have a client, and you will see shortly what is the ROS Pi API that you want to use in order to declare a node as a server or a client. And so we previously know that the way communication is handled in ROS is that if someone wants to publish to a particular topic, it registers the topic, and the master will open some TCP channel. And you see in the node sometimes the port of that virtual TCP channel is also displayed. And then you can have many subscribers to that topic. In fact, you can even have multiple publishers who are publishing a particular type of message for each topic. So we've already covered this. Point is that this is sort of asynchronous because there is some rate at which the node is set to be publishing, but the rate at which the subscriber listens and responds, there is no guarantee it will match the rate of the publication. Sometimes packages can compete for the same topic and things like that. And as opposed to this, in the server client configuration, you have similar registration process, but the difference is that there is no sort of TCP channel anymore. When a node declares that it wants to provide a service, that service is registered, and the client will request a service, and then just like in ROS topics, the master will first check whether the service is even running or not. And if it is running, then it has this bidirectional communication where you have a targeted message or a request to the server from the client, and then the server has to respond to that request. And right now, we don't care too much as to what is the timing of this back and forth. It's a very, this may be one of these things which come to mind, that what governs that my request has to be responded within some given amount of time, or can there be a pending request? So those are all good questions, and once we get to the code, we will answer those. But right now, I'm just talking about the high-level idea of a server client. This is a very popular communication model, and ROS also supports it. So how does it work underneath the hood? Just like we've discussed before, right? So when you declare or import some message library, that Catkin build system, when it's compiling your code, it's providing you that library or that data structure as a class. And you can create handles to that class and create new message packets, empty packets, and fill them in different sort of ways. So similar to that, services are also compiled by the Catkin build system, and it converts your .srv file into a bunch of classes. Okay, so you have your package, and then we create a new directory called service, within which we have foo.srv. When we run Catkin make, it's going to automatically provide 3 classes. One is the actual name of this service class. The other is a special class called request, and the last one is response, because every sort of service usage or communication has this request and response attributes to it. And so you will see how we have to declare our .srv file for this to work. So here's one example. We'll play with this in the lab. So I don't know if this is already pushed to Git or not, but so this is. This is a very simple file. It's adapted from the ROS tutorials, where the top half above these dash lines is your request, and the bottom is the response in the same file. And so what we are saying is that the request must be in the form of 64-bit integers, and they will be assigned to the fields A and B, and the response is another 64-bit integer assigned to a field called sum. So once we add this file to our workspace and run Catkin make, underneath the hood, ROS will create 3 classes for us to use in our code with the ROS Python library, very similar to how messages were being used. Okay, so let's take a look at how do you use that, and I'm going to go over this because I'm going to go over this a little bit faster because I want to also cover ROS launch, but more importantly, we will do a hands-on exercise on the ROS services in the lab session. So we will cover this again. So first, let me tell you how does the client side look. Okay, we'll take a look at the server later, but assuming there is a service running, if you want your node to act as a client, the way you can do that is by invoking this service proxy handle of ROS-PY, and the argument to this service proxy is the name of the service, the name of the service class. So in that case, in the previous example, that would be add two integers, and we'll get to what these other two arguments are, but we need to provide at least these two, and they can be set to default, and things will not break down. And so just like in publishing subscribing, we had these checks of whether a node is alive or whether your node is spinning or not, or there was a is shutdown flag. There's a good practice to also have a wait for service handle, which will or block the execution of the code with timeout period. ROS master says this service is not even active. Make sense? So wait for service is essentially going to check whether the service that you are trying to invoke, because you are a client right now, not the server. We'll take a look at the server in a second. Before invoking that service, you must check whether this service is even available. And so wait for service accomplishes that part. So the typical workflow of a client is you can call a service by creating ROS-PY service proxy with the name. We will often call this before even part one. And if the service returns an error, then just like you can handle an exception in the regular ROS node, in this case as well, you can have a special part of your code where the availability of the service can be handled as an exception. Right. So here's the actual code. So we are first saying ROS-PY. This is the code for the client. So I'm saying ROS-PY wait for the service, and the name of the service is add two integers. So I'm waiting for this, and none of these things are getting executed if this returns some exception. If not, then I actually create an instance called add two integers and tell it that this is a request to this service of this service class add two ints. And I know by definition of the service class that the request needs to have two fields, A and B. So when I actually create my request, or I create a variable response and I say send a request add two integers, and I'll send the values of x and y, whatever is in the code. This is not the whole script, obviously. And this service should return the sum which will be stored in the response. Okay, so the take home message is that the client uses a function called ROS-PY service proxy, and a client needs to wait for service before invoking any kind of requests. So it is a slightly different than a subscriber, because the subscriber is always listening for a topic. Whereas in this case, we only send a request and then expect a response. Okay, so this is the part which I said is very similar to messages. So just like we covered, there are different ways of constructing a message. One way is where you create an empty message type and then fill in all the fields. Another way, sort of what we used, was what is called in-order arguments. So when you are invoking the service, you have to provide a value for all the fields of the request of the service. And the other is the keyword argument, where you can provide the value for a specific field of the service class, and the others will be set to 0. Okay, so I hope you recall this from the message, which is why I'm not going to go over this in detail. Right, so this is how these requests are getting handled. So let's actually look at some more examples to wrap our heads around how to use this. So we need a .srv file, which will reside in another special subdirectory in your package. Typically, these files support all the commonly used variable types. There is provision to make it more complex, but for the most part on this course, we limit ourselves to what's shown here. So the way you can do this is simply create a subdirectory, and so this is my new file in that subdirectory. And once I have created this, I can do catkin make source, and this will be available. The classes will be available. Very important that when we invoke the use of this service custom file, we have to tell our build system where this file is located. Okay, so how does Catkin know that I have to create a class ROS Python for you to use in your code based on this response and sort of a request response structure of the .srv? We tell the CMake list, first of all, you have a dependency on what is called message generation. So these are already, by the way, provided in the template. We are just commenting them out. And in the CMake list file, we are also telling the path that you add the service files called add2integers.srv. So this is how the build system knows it must take this as an input and produce the targeted classes. So let's go over the entire code, just line by line as we did previously. I think that helps. So here is an example of the server. We haven't seen how to use the ROS Python API in the server, but here's an example. So let's begin at the very bottom actually. So this is the main thread or the main function in the server. It's not doing anything but calling another function called add2integerServer, which is defined here. Okay, so let's sort of parse out what this is doing. So first we declare our node. So we say ROS_PY init node, and the name of the node is add2integers. This is like a regular ROS node. You can choose to have anonymous true or false and all those attributes as well. And then in order for us to tell ROS that this node can provide a service, the API call is rospy.service. So to invoke, or for the client side, it's called rospy.proxy service. And if you are a server, you simply declare that I want to offer a service called add2integers, and this will use the service class add2int. So how do I know where this class is? We know where this class is because we are importing from beginnertutorials.service, we are importing all custom classes, and Catkin knows the add2integer.serve file exists, so it will know what this means in the code, add2ints, based on that. Okay, and what we are saying is that this service is such that when we receive a request, remember this is a server, if we receive a request, we have a callback to handle the request, similar to like a subscriber. Okay, so we can, when we receive a request, we will call handle, we'll call this the callback function. The arguments to this callback function, as you can tell, we are reading out the .a and .b fields of the request message. How do we know that the name of the field is .a and .b? Because we know the definition of the class. And so we can simply read our request packet or the request sort of client request. We add them together, and we are returning the sum of these two fields. And look, I'm again using a service class, which I haven't defined anywhere, but ROS knows about it because it created this add2integers class. It created add2integers request and add2integers response as well. And so I'm simply saying whatever whatever is the result, add2integers response means this will be allocated to the sum field of the response. And again, it's a little bit difficult to visualize all these pieces, but this is the most straightforward example of using the service request. Okay, so I had annotations too. All the requests are sent to the handle, and this is a regular node, so we need to keep it alive. So we add ROS_PY spin, or you can have all of this into while is shut down, keep responding to requests. Yes. It's automatically made available to you. I think if we go all the way back, or we don't have to go all the way back, Yeah, since the CMake knows that this is the definition of the .srv file, and we know that this is the request field and this is the response, that's all we have to do. Once you have run catkin build, ROS will know what this means because it will be created. Okay, so what does a client look like? And it can be made to look much simpler, but I'll tell you the key parts of the client. So here's the first, what you may find surprising part. The client does not necessarily have to be a ROS node. Okay? So you can actually, we've seen an example of this, that when we request Turtlesim to clear or to reset or to teleport absolute, these are all service requests to the Turtlesim node, but they are being sent directly from the command line. There was no Python ROS node we had to create to make requests to this Turtlesim server. So that's the first part. It doesn't have to be. It can be. It doesn't have to necessarily be a node. So you don't even have to call ROS init node in this example. And so this is the example of the client. And so here's where the interesting stuff is happening. This is just a check to make sure that when you are requesting this service, you have to provide values of the x and y variable that have to be added together. So this is just a check to ensure that you are following that format. If not, then we prompt you to follow a certain format. But the client stuff happens here in this function. So like I said, the client has to first wait for the service. So we are saying wait for the service add to integers, which is essentially checking whether this actually is available at any time. And then the actual request is made here with ROS-PY service proxy. So right here, and we say add to integers. This is the name of the service that we would want the request to be made. This is the class of the service. And then I'm using the explicit style of invoking the service by providing the value of x and y. And then how do I know that the response will create a field called .sum? Because I know, again, the class structure of this custom service. So I can just read out the value of sum and display this variable response.1. So any questions on what the purpose of services is? The syntax, again, like with many other things, you don't have to remember, but we'll see an example. We'll provide you this template of add to integers and similar stuff that you will use in your lab session. Okay, so once again, when we add these two nodes, we make them executable. Same thing. We have to compile, do catkin make on our workspace before running these nodes. And I might be able to show you an example that we will do in the lab later. So just to remember at a high level, when you are dealing with topics, the constructs is called messages. The data type is in the form of a message. It has a .message file. It has all these ways of constructing a message, and you need ROS message to interact with these messages. When you are dealing with services, the data type is in form of ROS service. Okay, so it supports similar kind of functionalities as the ROS message supports. I think I have an example from Turtlesim. So we have seen this list before. These are all the services offered by Turtlesim. Some of them you will use for your assignment 1 as well. And so if we say, what is the type of service which is to clear the ocean or to spawn the ocean. So here's an example. So previously we have seen, how do you say ROS message type and say messages. I will show you the exact message directory that is used by Turtlesim. Here we are doing the same thing, but for a particular type of service. So let's parse this command. We are saying what is the type of service associated with spawn, and whatever is the result, just send it to ROS service show. So essentially show me the actual .srv file associated with spawn. And so you can see here, to spawn a turtle, the service needs to be sent a value x, y, and orientation. Plus, there's also a request field called string name. So I can actually name my turtle by providing some value to this service. And the output of this is some handle to a turtle with the same name as this string. So for example, I can say ROS service call spawn xy theta and the name of the turtle, and in the same ocean a new turtle is spawned at 3,3 with the orientation 0.2, so it's slightly tilted compared to the default turtle. And when you look at ROS topic, this turtle will not be called turtle1, it will be called new turtle. And so one of the things we will do in our lab session is the following. We will actually have multiple Turtlesims, and we will use a service to spawn many turtles and even stitch them together so that they can mimic the behavior of each other, to make all of these concepts become slightly more clear. Okay, so that was all I wanted to cover about ROS services, but since we have time, I will cover, or at least start talking about launch files. And that's something that you will also use if you want to attempt the extra credit for assignment 1. So why do we need launch files? The motivation is kind of what is shown here, that even within our simple life so far, which mostly involves ROS core, Turtlesim, and maybe one or two other nodes to interact, and maybe RQT to view, you can see how there can be a lot of clutter when you not only launch these things, but sometimes there's a desired sequence in which these nodes also need to be launched, because it might not make sense to launch one node which requires some messages from a node which hasn't even been launched yet, or is launched out of sequence. So first few messages might not be relevant, or they may get dropped. So our RQT graphs also become very complicated, and the main point is that it becomes quite painful to launch everything manually and remember the order in which things have to be launched. So this is some arbitrary example. Here's actually the RQT graph of the F110 car. So you can see everything in oval is like a node, and all the square things are name of topics. So we have at least a dozen nodes which have to be launched in some particular order for the car to respond to your sort of autonomous navigation intention. And so to circumvent this problem of keeping track of what to launch, execute in what order, ROS supports a very good functionality called ROS launch. It's a tool that we will use many times, especially when we interact with more complicated packages like mapping, and localization, and all the interesting stuff that we'll get to in the next half of the course. And so the format of this command is simply ROS launch, name of the file, dot launch. So the file has a dot launch sort of extension, and we have to provide the package to which it belongs as well. So I misspoke. It's ROS launch, name of the package, and then the name of the file dot launch. So you can think of this launch file as a file to launch other nodes. And that's only one of the things that it can do. It can do many more things. It can configure these nodes. It can accept arguments when we launch. So you can have different behaviors in the resulting nodes which are launched. And it will also be a chance to set some parameters. We haven't spoken about parameters yet because it doesn't make sense to introduce that for the Turtlesim, but sometimes, for example, when you want to launch a sequence of nodes which are responsible for mapping, there are some parameters which are thinking what should be the width of a grid cell in the map. Keep track, maybe centations, but it is more memory and computation intensive. So you may want to play with that grid size, and you will play with that in your launch file. So that's a parameter. Okay, so we can launch different nodes, and we can launch what is called parameter server, which are these fixed arguments that that are passed on as a pre-configuration to some of these nodes which are launched. And a launch file can even launch other launch files. So it's you can stack them, and you can literally have a file called wall following.launch, and your car will make sure everything is launched in a sequence, and your F110 car can go around the loop following the left and right wall and not crashing. Okay, so in fact, that's also one of the labs that we'll work on. Okay, so if we can launch files from other launch files, we haven't seen an example of a launch file yet. The things that you add in the launch file are executed in order. So this is where you can make sure that whatever order is required for your robot / F110 car to work, it is adhered to in the launch sequence. It can accept parameters and arguments. You can even perform some operations. So you can say that start logging all the data if this topic exists in the background. Otherwise, don't log it. Okay, so just some sort of a checks that you can do. So let's take a very simple example of what are the constituent things that make up a launch file. So I'll break this up. So a launch file is like a markup language that ROS recognizes. It is heavily inspired from XML. So you have all these familiar things like there are some definitions of certain tags, and you invoke a tag, you define some attributes, and then you close that tag. And so this markup language, when put together, becomes a launch file. So every launch file must begin with this launch tag, which tells ROS that this is a launch file. So here's one example. What this is showing is, and we'll do this in the lab as well, you can create some groups, and a group is nothing but assembly of parameters / nodes which functionally are tied together. Okay, there is no definition of which node belongs to which group. It's up to the user, and groups are ways to organize your ROS launch. So a real world example would be that in your launch file, going back to the wall following example, you will have a group called perception, where you will launch the LiDAR node. You will launch some other node to process the messages from the LiDAR. Maybe just prune messages which are only in the forward-looking direction and not in the entire field of view. So these are nodes which need to work together on a small specific function. And so it makes sense to launch them into a group. And what you can also specify, and that's peculiar to Turtlesim and other nodes, in the group tag, you can specify what is called the namespace of that entire group. So remember how I told you that if you launch a node which has the same name as a current node, the previous node dies. We even saw an example of that. Here's a way to avoid that. So when I launch my first Turtlesim node, so here's a tag called node, and the arguments are I have to tell the name of the package and the name of the node in that package in the launch file. And I'm telling that the first Turtlesim belongs to a group with the namespace Turtlesim1. Why does it matter? Because I can create another group called Turtlesim2 and launch a separate ocean inside this, and my first ocean will not die, even though technically both are Turtlesim, and they are using Turtlesim_node to launch their own oceans, but their namespaces are different. So this is one of the things in the lab session that we have an exercise on to make sure you understand this concept. But going back to why we are dealing with this, in the launch file you have a group, you have some node. This is how you launch a node. You have to provide the package, the name. Sometimes you also have to provide parameters to the node. So here's another package that you haven't seen, but this package is called Mimic. It is also offered by Turtlesim. Sorry, this node is called Mimic. And notice that every node doesn't need its own group. Some nodes you can just launch directly, without grouping them. So here's an example where we provide the Turtlesim package. The name of the node is Mimic. The topic is also Mimic. The name of the file is also Mimic. And without going into too much detail, what this is doing is it's launching a node called Mimic. And what this node does is it has an input field and an output field. And what it does is whatever you tag to the input field, it will publish to the output field. So it's like a replay node or a relay node. So what we are doing is we are telling it, read the inputs from the first Turtlesim session and send them to the next Turtlesim session, or map them to the next Turtlesim session. And that's not the this fine detail the point of this particular slide. This is just to show you an example of the launch file, and then we can close this. So, our launch file in this example is doing three things. It's creating a group called Turtlesim1, which launches an ocean. It does the same thing for Turtlesim2, and then it remaps using this mimic node in the Turtlesim package. But notice, nowhere in my launch file did I say that you have to start ROS core, which is the first thing we always have to do. And that's another reason to use launch files, because when you say ROS launch, package name, launch file, ROS core is automatically started as the very first thing. It's implied that when you are launching something, ROS core has to be started. If ROS core is already started and you launch a file, it won't start a new ROS core session as well. It's smart enough to know that it's already in the background. Let me just launch these nodes in sequence. So when we say that in your assignment 1, you have to have launch files for each of the problems, what we expect is, don't worry about the groups too much, but what we expect is you will have a launch file in which you will launch the Turtlesim node, you will launch your own node, and maybe even pass arguments whenever required to that. And you don't have to then, when you demo, you don't have to run ROS core every time. You can simply say ROS launch, name of your launch file, and it will launch everything necessary for that part of the problem. Yeah, so if we actually launch the file that we just saw, and this is again, we'll do this in the lab session. It says ROS launch, name of the package is beginner tutorials, and then we say turtle mimic.launch. It launches 2 oceans. And then we've seen this before, that we can directly publish to one of the turtles command velocity. So we've seen how to rotate this turtle in a circle. This was one of the lab sessions. But what happens is, even though we are publishing to Turtlesim1, notice how this becomes Turtlesim1 and not just Turtlesim because of the namespace. Even though we are publishing to Turtlesim1, the second turtle will mimic the motions of the first turtle. And just as a fun exercise, you can see if there's a lag in the two, or you can see if both are respecting the same ROS topic hertz, because there is some cycles consumed by the mimic node as well. So there should be some lag, but we can verify. This is probably too poor of a color choice to be displayed, but here's an example. Again, the details are not that relevant, but here's an example of a launch file on the F1tenth car. Like I said, many research cars, we just have a single launch file called race.launch, and it does a bunch of different stuff. It's a long file, but it saves us the trouble of starting things in order, right? So it's a very demo-friendly way of working on robots. So ROS launch is very, very important in robotics, and people use it all the time. This becomes the de facto way of interacting with your robot after a certain point, because you don't want to go and change stuff in the node every time. So by the end of this course, hopefully we'll show you by demonstration and through these assignments to get into the habit that even when you write your nodes, you can write them in a way that they can accept arguments when they are launched, rather than every time going into the node and recompiling and things like that. So this is just general software development practice, but ROS embraces that through the ROS launch functionality. Okay, so instead of going into ROS bags, let me maybe take 5 minutes to show you some examples of stuff we will do in the lab session. All right, so first let's look at the ROS services. So ROS code is running, and then let me actually show you a bigger window so it's clear. So first I'm going to CD into my beginner tutorials. This might not work if you are following along right now. You don't have to, because there's a dedicated session. And within beginner tutorials, there's a new directory called SRV. In fact, there's another subdirectory called launch that all this will be pushed to the Git repo before the next lab session. But within the service subdirectory, we have our custom file add2integers.srv. Okay, so we already know what this file is, but very, very quickly, it's a very simple file. The request is 2 integers and the response is the sum field. And so where are the Python nodes which are the server and the client? They are also in beginner tutorials. So let me clear all this. If we just go back and then now go to our usual familiar scripts folder where all the Python scripts reside. So here you can see previously we only had listener and talker. Now we will have the client and the server as well. Okay, and for the sake of completeness, very, very quickly, the server just has one function. We initialize this node as a server. Remember, server has to be a node. The client is optional, whether or not that's a node. We use ROS by service. We say this is the service we want to offer, add2integers. This is the class. We know about this because of our edits in the CMake file. And this is the callback function when an actual request is received to the server from some client. And the response is just the sum of the fields of the request. So now let's actually run it. So I can say ROS run. Name of the package is beginner tutorials. And I'll say add2integers server. So my server is running. It says ready to add 2 integers. And now let me use the client to actually invoke a service. So I can say ROS run beginner tutorials add2integers client. And notice that if I just run this, it will throw an error. Okay, and it's telling me that I'm not using the correct format of the client. This is the part at the bottom of the client which we didn't go over detail, but this is an easy fix because now I can say just as 22 plus 33. So the request was sent, and you can see the server also said I'm returning this sum. So this was the request response, unlike the publishing subscribing, because in the publisher subscriber there's no feedback. You just publish and you don't care who's subscribing. But here you can see as we issue the request 22 plus 33, it was sent to the server and it has to respond, and it actually responded very, very quickly. Okay, so we'll do this and more in our lab session, but before we close for the day, let me also show you I can simply say ROS launch beginner tutorials turtlemimic.launch. This is the launch file that we just saw. So with this, and notice how my ROS code is closed right now. And if I just launch this, everything is launched on its own in a single command. And so right now, instead of moving in circles, I am pressing some arrow keys. It's sending messages to one of the turtles, but the second one is mimicking that. And that's not the point. The point is that they are connected because of a single launch file. And everything was launched in one go. Okay, so this was a very, very quick, fast overview. We will take a look at some more examples of this, ones which are very relevant to your assignment. We'll also resume and take a look at what is called namespace handling. So this idea that you can launch similar nodes with different groups and different namespaces. I think that's also important for you to know before we start working on the car. And that's all I wanted to cover today. So I'll see you on Thursday.